Hello and welcome everyone to the Edge AI Talks. Today, Rethinking Silicon, the new architecture of low power AI. Joining me today is our good friend Danilo. Danilo, how are you?
I'm fine. Thanks, Ed, to include me. It's great to be with you today.
It's wonderful to have you here. As just for the audience to know, Danilo is a great friend of the foundation and has an incredible background as a technical director, a professor, and even an IEEE fellow. We're very lucky to have him here today. Danilo, I believe you're celebrating today, right?
Yeah, it's Epiphany in Milan, in Italy. Yeah.
Excellent, excellent. And of course, we're all celebrating the new year. This is a time when it feels very energized for what's coming. CES started this week. In fact, our special guest today will be calling in from CES. And I feel like there's an incredible conversation around the power of AI, but not nearly enough conversation about powering AI. So the fact that we get to have Danilo and our special guest GP with us today to talk about how we rethink low power solutions for artificial intelligence is really exciting. Danilo, any additional thoughts? Excellent. Well,
No, you covered very, very well. It's great to have a GP Singh here with us and look forward for his great talk.
well, let's see if we can catch him. I know he's at CES today. Why don't we bring in GP Singh, CEO of Ambient Scientific? GP, can you hear us?
Yes, Ed, thank you very much. Ed and Danilo, very nice to meet you guys. And thank
It's
you for
Nice to
calling
meet
me
you.
here.
We were just saying that your timing is fantastic. Everyone's looking at the new year. New Year's make you think of new possibilities. And it feels like this area of rethinking AI and thinking about how we can achieve our solutions in a much more efficient power envelope is a very strong conversation. What have you brought for us to talk about today?
Yes, that is the topic I mean, I have prepared. Uh, See, the AI today, there are many bottlenecks. One of them is the chip on which all this the software is running, whether it's AI or assisting AI. So we'll focus today on that chip or the silicon, as we geeks call. So we'll discuss silicon and what is there in silicon and how can we make it better for the current and future AI. I'll discuss about that.
Okay, well, working on AI, geeks, or I like to call them the cool kids, but everybody has their own opinion. Why don't we let GP take it from here? I will suggest that we are collecting comments from the audience, and we will be saving time at the end to address some of those comments. So please feel free to submit them. But I know GP, you've got a lot to share with us today, so why don't we jump in?
All right. Thank you so much, Ed and Danilo, for giving me the screen and the platform and the opportunity. Hello, everyone. I have to actually ask for a lot of forgiveness in advance. I had built this slide more as a tutorial to my own team, and this is almost 3 hours long, the original version, not the today's version. And the reason is that it really there are so many problems that one needs to go through or to really understand what Ambient as a team is doing. So I have built this slide deck mostly as a kind of a very basic level tutorial style talking. So it'll be more of a conversation. I ask for forgiveness in advance if there are advanced audience there who are looking for far more advanced topics. I'll be available offline if you do want to discuss more advanced topics. I want to start, Ed and Danilo and the team, with this very simple statement, which was given by this probably is not the exact form of the statement, but what it says is if you have an hour to solve a problem, 55 minutes or a big part of that you should spend analyzing the problem or understanding what the problem really is. And that's what I have built this slide really as, or the slide deck really as, is to understand what the problem is. Today we will focus only on silicon. What is really there in building a silicon for AI. So let's get started in trying to figure out the problem first. If there are questions, we can, I'll really appreciate if you can hold them. If you really feel that there's something urgently you need to tell, that's fine. We'll be okay to interrupt. Is that okay, guys? All right. So with this in mind, what is a computer? What is computing? For me, computer is actually very simple. And start with just simple a plus b, a minus b, a multiplied by b, and a divided by b. This is really what a computer solves. This every elementary school kid also solves this problem. So there's, from my point of view, computer does not do anything special. When we needed to automate this computing, you see on the left hand side, there was a device called Viscus that was invented in old cultures. Many old cultures invented it in one or other form. When things became a little bit more convenient, we ended up inventing a calculator. And here you basically enter an operand. You basically enter A and B. You press a function and then you read an answer on the display. This works very well. All of us have used it in our career life schools. Now, what happens if the same number of calculations or number of functions that I need to compute becomes 100 million calculations? Can a calculator handle this? Answer is no, because it will become very difficult, very error prone, tricky to verify results, because the results have to be just viewed one by one, and it will be extremely time consuming, right? So to solve this problem, we ended up inventing a little bit more computing. However, before we go there, I just want to bring this statement. Need for faster computing at the cheapest price is perpetual and growing, and it has been growing since I was in school, and I'm sure this has been growing much before that. So one thing that has been always constant is that by the time we actually build computers, the need for more speed at cheaper price grows even more. So it's never ending problem. Anyway, come to our simple calculator. If I wanted to convert this simple calculator into a computer, what would I do? I will have to put automatic flow control. Means rather than entering these numbers manually, it will be great if these numbers were entered automatically somewhere, and whether it's plus or minus or divide or some other functions that need to happen, that was done automatically. So automatic flow control. It will be great if there was a storage for the operands that need to go in there. This basically becomes an advanced calculator. And then it will also be nice to have an output which goes in somewhere automatically. And it will also be nice if the output gets verified somehow before it gets used. So this is a basic shape of a computer. All computers in the world are actually built to solve this fundamental problem. Automatic flow control, operands, input, output, and lots of functionality. Now, this universal computer, it all comes down to performance versus price. Why? Because there are many forms of input. How do I put input operands? I can put it through a punch card, which started in the beginning, hard disk, SRAM, network, DRAM, CD, DVD, floppy disk, and others. Similarly, what we call arithmetic logic unit, which is basically the basic form for computer. And the automatic control, we can call this as an ALU for now. And then we put the results. Most of the time results go either into a print device or into a display device or a network device or a storage device. Again, as a storage, we can use so many features. Any computer can have one or many type of these components. What determines what is picked is basically the price. So price and the need. So somebody has a particular need, is willing to pay the price, you'll pick up those components. So as we talked, so a little bit more about computers and how we choose them. The requirements or the need, which is capacity or the speed and efficiency, and the most important of them is the last bullet point, as cheap as possible. This is the basic need. Based on that, we will pick these components. A lot of these, of course, are determined by business needs. If the end business is the consumer, then just determined by the price and the functionality or the performance per price or per unit price determines what goes in a computer. Now, let's try to get it down to the chip. We all know that all of the computing happens in chips, whether that's the fundamental logic computing or network computing or storage computing. There is always a silicon behind every one of these small or large functions that we are doing. That silicon can be as big as an NVIDIA chip that or NVIDIA-based data center or CPU-based data center that takes a football field, or it is just the watch on your hand. All of them are form of computer. So let's get down to a chip. Inside the chip, we will have the ALU, as we call the compute unit, which has the flow control also. And there is, let's say, an input device and an output device. A typical ALU today can run at the speed of 1 nanosecond. Means if I want to do add function, multiply function, I want to do divide function, or many other functions can be done in 1 nanosecond, even all the way down to 0.3 nanosecond, 0.2 nanosecond. I happened to be part of a project in past where this ALU was taking only 100 picosecond and the computer was running at 10 gigahertz, but that's only one example. So this can go very fast. And that means I can do one function in every 100 milliseconds. Okay. Another way to look at it, I can do 10 functions every, I can do 100 million functions in 100 milliseconds. This is very good. This can happen very fast, assuming that my input was coming from hard disk. Let me see if I can draw here. I can. If my input was coming as fast as my flow controller, the ALU was functioning, or my output was absorbed as fast as my ALU is computing. So when you go down to those numbers, really, actually a hard disk takes 10 to 30 milliseconds to function. This is the cheapest storage available. And if I was to do 100 million of just the calculation, basic calculation, this could take up to 1.2 to 3.5 months to do. That's too long. That means the computer is too fast. By the way, just for a reference, 100 million calculations are actually too little. Very little amount of computing will happen in 100 million calculations in today's world. In today's world, we do billions and billions of operations every second. So this is too slow. If I wanted to build my computer, the simple computer where I have a hard disk as an input, hard disk as an output, and ALU as a functional unit. So make it faster. How do I make it faster? Well, whatever has the problem, those are the areas we are going to improve. So the flow control, input operand, output operand. If I was to replace those by DRAM, we can run these DRAMs up to 100 nanoseconds. Okay, this will give me 100 million calculations in 30 seconds. This may be okay. Well, not in modern world, but in some simple cases, this might be acceptable. If I want to go even faster, or let's change the problem, if I have 1 million functions, 100 million of them means rather than one function, each calculation required 100 million functions. Then the same thing, even using DRAM, would end up taking 11, 12 months, almost a year. Not good. Now, if you look at today's world of AI, the storage memory needed for one record can go up to in tens of gigabytes. And for multiple records, it can go very, very, the storage requirement can go very high. So we want to make it faster. What do? I replace those DRAMs now with SRAM. If you were to replace them with SRAM devices, if you make very fast SRAM, they are capable of running at 1 nanosecond. This will give me faster processing time, and one function can run in 0.4 seconds. 1 million functions. When I say 1 million functions, 100 million calculations, it still will end up taking 111 hours, around 100 hours. It's still not as fast as I want, right? So if you look at the current current devices that are available, the SRAM, the ALU, they can go up to 0.3 nanosecond. And how are we doing with time? Okay, I think. And we'll be able to compute this 100 million calculation, each having 1 million function in 33 hours. Okay, fine. What if I want to go even faster? Well, at the component level, at least, like this is storage and ALU, we have run out of gas. And now the problem is given to the chip designers. If you want to go even faster than this, the problem has to be solved by chip designers. Two parts of chip. That's basically a computer architecture, which is mostly based on the circuits that they use, and the circuits are based on the actual material or the transistors and the resistance that we use. So making computers fast using not so fast components. This is really, in my language, that is what a computer architecture is. Because as we just saw, if we were to use a very simple computer, I am not going to get the speed and the feed that we are looking for. Just to give an idea, we were only talking about 1 million functions and 100 million calculations. If you look at an LLM today, it is 100 to 500 gigabytes. Now we started constructing a smaller LLMs nowadays, can get into a few gigabytes also. But the number of operations are in billions and trillions. So whatever calculation we were doing, as you can see, if we were to use a very simple computer, that's not going to be useful for AI functionality. A little bit more about idea about, okay, so when we want to start using these components, hard disk, flash, DRAM, SRAM, and the logic chips. The logic chips are extremely expensive, the most expensive. Though when you listen to the business people, they will say DRAM is the most expensive component. Actually not. It is the logic transistors and SRAM that are the most expensive inside the chip. And I have listed the pricing. These are all approximate numbers. Don't quote me on this, but this will be this can serve as a good guideline. SRAM generally is very, very expensive. If I wanted to get 500 gigabyte model into SRAM, you're looking at around $500K to $5 million, depending on what type of SRAM you want to use. If you want to use SRAM that runs very fast, 0.2 nanosecond, you're looking at spending $5 million just for the storage of one LLM model. Not good. So we cannot use just one of these components because of the speed or the price. So we have to do mix and match. Let's some do. I wanted to put this slide up there. I'll spend that you guys also read it. See, I'm going to put some statements here. I find that a lot of time people find it very controversial, but I'm comfortable. See, most of the components that we use in semiconductor, they were all invented by 1990s. In past 25 to 30 years, we as an engineering community have not invented anything fundamental. Like we were talking about SRAM, DRAM, HDD, SDD. Nothing fundamental has been invented in past 30 years that can help AI computing. We have invented a lot of methods to put these components together, but not the fundamental components themselves. Now, the problem is that AI is a very disruptive compute paradigm, but it also needs a more fundamental component level, material level innovation, like new transistors, now like the new storage structures, like the new wiring structures on chip, probably a new material for the chip. So far, I have not seen anything promising. There was something called graphene that was quite promising for some time, but looks like we are not able to manufacture them. In my opinion, quantum computing is at least 40 to 50 years away for a common person's use. It will get into a specialized usage much before that, but for a common person, for people like me and you, it will be, I think it is still 40 to 50 years away. So still something new comes up from component engineering or from material scientists. We are left with only optimization tools to make these computers faster, more efficient, affordable for the new AI paradigms that are starting, the Gen AI, the agentic AI, where you want to have almost human-like computer running into a small humanoid or a small gadget or even a watch for that matter. So computer architecture and circuit, this is the art of building perfect solutions. Perfect solution means having the speed and feed, but using imperfect components. We come back to those problems again. So first, one thing that we use is called parallel computing. This is one of the tools that computer architecture uses, where we can put multiple components together to work. So if I was to use, for example, if I have two functions and they're not dependent on each other, we will be able to put them on two separate ALUs, and will be so this is the concept of parallel computing, basically using multiple parallel computing cores which have their own flow control. They have own way to get the input and output and have their own independent functionality. Parallel computing, just I was invented in 1950s. It's one of the tools used heavily in AI, invented long time ago. AI in a simple world is a massively parallel computing. So what you will call hyper threading computing. CPUs, they try to do parallel computing using what we call multi-issue pipelines. The DSPs are another example of parallel computing. As you go from left to right, you will see the computing, or the number of threads that are computing, or the number of computes that are happening parallelly keeps going up. NPU, which is the workhorse for neural networks or the AI, need to have humongous amount of parallelism. Ambient Scientific's DGAN engine or some other examples will be Samba, Nova, Grok, GraphCore, these guys, GPUs. They are massively parallel computes. The parallel computing brings their own challenges. In general, if it was up to us, we would like to put billions of these compute units on one chip, because at the end of the day, as many of computes you can put in one chip, that's the cheapest and easiest option. The moment we have to split a problem into multiple chips, the problem generally goes up by 10x. The magnitude of the problem is exponentially more. So we would like to put billions of core on a chip, but we cannot because we run out of chip area. Another important thing about AI is that 95% of compute in AI is just multiply, accumulate. So a single inference of LLM, hundreds of billions of MAC operation, it also requires tens of gigabytes of operands. So the second problem, even if you're able to solve the MAC problem, for example, ambient has solved in one way, other people have also solved in different ways. Of course, we claim our way is best. Sorry for that marketing bite there. But all of these compute units need to have operands on, and those operands can only come from some storage unit. Ideally, we would have wanted to put tens, hundreds of gigabytes of storage on one chip, but it is not possible, again, because we have not invented those components or those materials wherein we can put hundreds of gigabytes of operands or storage into one chip, and that presents a huge problem. Another, so the problem, the storage problem we solve by using a concept that is called caching. Unfortunately, I don't have too much time to get into caching. This is one of the greatest technology that was invented. It was invented quite a while ago. Sorry. So the problems we see with the memory is, the summary is listed here. SRAM, they are fast, but they cannot be large. DRAM, HDD, SDD, they can be large, but they cannot be fast. AI requires large, fast memory. That means there is no memory that can get on one chip for AI computing and is ideal for AI computing. And that is one of the biggest headaches that we have to solve as computer architects. We'll come back to some of the limitations. So demand for more performance keeps growing up. Why I put that on the top is because building a chip generally can take up many years. And by the time you're done building your chip, your current need has changed. That means chip designers always have to build for future. But what is the future? Nobody knows. So the hardware people, chip design people especially, have to bet heavily, and most of the time they have to bet on just their own opinion. DRAM and SRAM and logic cannot be built on same die. Sorry for this typo here. This should have been comma. DRAM, SRAM and logic cannot be built on the same die. That means if I would want to use large storage, which will be DRAM or HDD, it has to be outside my logic chip where the compute is. Outside is a big headache. The die size is limited to 850 millimeter square. Today, there is no technology that I see on horizon that can increase this die size substantially. Little bit increase possible through optimization, but not a lot. So we do use what is called a die shrink, or the next technology node, or the technology shrink, that does give us more capacity, but not nearly as much as AI wants. One of the biggest problem of the current technology, silicon technology, the on-chip wires are extremely slow. On an estimate, on my estimate, the wires actually have slowed down. In past 30 years, they have slowed down by 30 to 40 times. SRAM can be built on the same ALU, but the size is limited. Stacking chips has a lot of limitations, and nowadays we are facing a new monster, that is heating. Heating has become such a huge problem that most of the industry is just trying to solve heating problem. Caching structure very quickly is a small memory, faster memory, closer to the compute, slower memory, farther from the compute. And as we go farther away, the memory size increases, but the speed degrades. So how do we keep computing when my operands are not available to me? This is the biggest problem for AI. I am sorry, in interest of time, because we are already crossed half an hour. In interest of time, I am going to skip three major discussions. One is the wires. Wires are actually a huge headache on the chip. They are huge headache on packages. They're huge headache on PCB, and they're even bigger headache from PCB to PCB or chassis to chassis. And you see a lot of these problems that happen. Of course, every problem is also an opportunity. So you will see in each area, many companies exist solving these problems. Pipelining is one of the most important tools that computer architecture uses for optimizing or hiding some of these problems that especially storage units present. Caching structure one needs to use with care, because make it more complicated, it will become almost unusable by software. Make it too simple, the speed and the price suffers big time. Getting into AI, what is it's generally represented as these circles and these arrows. Arrows are mostly weights, and the circles are the Mac compute, plus some more computing for activation. So pipelining, as you can see, between the neural networks is basically break a problem into multiple steps. And as you can see, it exists as a natural choice. So massive amount of pipelining is possible in neural networks or in AI computing. And obviously, we're computing millions and millions of these neurons, these circles called neurons. So it's a massively parallel computing problem. The challenges that are different in AI computing is basically one to many and many to one. You will not see this challenges presented in CPU or even GPU or graphics for that matter. In all of the CPU workload, these challenges are not presented as much. So the caching hierarchy or the pipelining structure that we have grown building for past 50 years around, they're not very useful in AI because of these two problems. Then we need lot of Mac computing, and we need to supply operands to them. Unfortunately, multipliers not good in digital implementation or Boolean algebra. See, Boolean algebra or digital, as I say, is great for everything except multiplication. Analog computing, if you can handle it, great for Mac computing, not good for anything else. Except some of the sensor operation. So this is another problem you, as an AI designer, one has to solve. If you have grown to be writing an RTL and putting A multiplied by B equal to C, and then pushing the synthesis button to build your chip, not a great starting point to have, because this are too many Macs and require too much storage, very different from the classical, both graphics as well as the normal compute problem. One of the idea that people use is that since I am computing multiple Macs here, I am going to just build a lot of these units together, or a lot of the compute units together. However, the problem generally comes. Oh, sorry. Hang on. problem comes is again one to many and many to one. As I said, one to many and many to one. As you can see, this is this problem prohibits or basically makes it very challenging to use independent parallel compute units putting together in the chip. Means one needs to have very special architecture to be able to feed operands and do that one to many and many to and or solve the one to many and many to one problem. One of the solutions that has been tried, many companies have been built. One very successful story got bought by NVIDIA called, you all know about Grok. It's called systolic array, where again, many parallel units lined up together exactly like the neural networks is. Theoretically, this maps very nicely to the neural network, except for many to one, one to many combination. And that's where systolic array will present a huge challenge. And most of that challenge is thrown out to the software. So if you are going to implement a systolic array, building the silicon is rather easy. The software is what needs to handle the problem. One of the common technique people have used or have tried to use is build the SRAM on each compute unit or each die, and then basically break the problem in such a way that all of the storage will come only in the SRAM. Sorry, I have not been able to get more into the caching hierarchy, and because of that, this may seem a little odd, but of course, the problems for L2 cache and L1 cache, those is still one has to handle. However, if somebody is trying to eliminate the DRAM by putting very large SRAM on chip, this is a good way to speed up. The only problem is it will be very, very, very expensive, and the operands, number of operands become limited. So one of the things we did not talk about is using quantization. Like people say, you can use 4-bit or 8-bit or even 2-bit operands for computing. That's another way to increase the number of parallel computes, but it comes at a heavy, heavy price of uncertainty and errors and unreliability. Excuse me. I'll just very quickly go into our ambient technology. We have tried to optimize, but we have optimized for all of these problems simultaneously. And I'll just discuss the architecture. So it's a little bit of a marketing here. Extremely flexible and configurable systolic array. We don't call it systolic array because systolic array becomes a software concept in our case. It fits very well for all of the deep learning algorithms, all of them, not just one. Even the future algorithms, our architecture is very well fitted for. And it can be configured vertically and horizontally. What it means is each core can combine in parallel with another core or can combine in serial with the other core. So it is a systolic array square. We have invented what we call digital analog in-memory computing. So in-memory computing, not purely analog, but a combination of digital and analog. This allows us humongous power saving when we are doing the Mac computing. So for Mac computing, we are able to use, as I said in past, analog is great for Mac computing, not as good for anything else. But again, AI 95% problem is Mac computing. It also reduces the physical size, which makes it better or solves the wiring problem. And it is very good fit for co-locating with the memory because the way this analog or digital analog combo works, you can build the analog computing using the same cells that are holding the storage or holding the operands themselves. So it eliminates wires, which is humongous help because, as I said, the wires have degraded by around 35x in past 15 years. They have degraded, means they have become slower. We have also created a concept called 3D memory. this 3D memory is able to feed many of layers or many neurons simultaneously and can help build very large or very small Mac computing. So it provides extreme flexibility, and it is very good for in-memory computing in general. Forgive me again for a marketing slide. We as a company have ended up inventing, starting from custom circuits. We built actually transistors. We have a good custom circuit team, which we have built transistor level up. And all of these custom circuits are built so that they can make the architecture far more efficient. Based on that, we built our architecture. Then we have the SoCs, actually many chips now. Most companies actually start at the architecture level or at SoC level. So we have gone deeper. The problem in going deeper is that all of the software or all of the tool paradigm that exists has to be tuned. So it becomes a massive software problem. However, we have been able to solve it. Our first chip is already in market. You can come to our booth, see us in CES, booth number 8263. And this chip will be available. We are designing the second chip. We are designing the third chip. These two are still in plan. And we have customer for all of this today. So we have been able to crack this code for efficiency, at least till we get to quantum computing. How it works is you will have input operand, converts into analog, do the Mac computing in analog. This is only a conceptual scheme. This you can find on internet everywhere. The good thing about this structure is, in our structure is, the input is digital, output is digital. So the software people have to do not know, they do not care, and they do not bother about knowing what is happening inside. For them, classical software, TensorFlow, or any other software structure is sufficient to program in our chip. That means this block is not available outside. Just to give you an idea, we have constructed what we call this DIGAN unit. So as we said, the Mac is happening along with the storage for the inputs themselves, and we are able to compute this entire structure today in our first chip in one cycle, which would have taken for a single core or single issue machine around 38,000 cycles. Of course, GPUs or more parallel machines can be faster. We are able to support, this is a byproduct of this DIGAN architecture. We are able to support 4-bit, 8-bit, 16-bit, and 32-bit integer in the first chip. In the second chip and third chip, we are also supporting floating point all the way to double float. This structure is able to do 256 Mac per cycle. In the second chip that we are building, this will go to around 2000 Mac per cycle, and the third chip will go to 4000 Mac per cycle. So you can see this is a hyper threaded, massively parallel machine. Make it even better, we are able to actually compute multiple layers by putting these operands here and the weights into another memory. This is the 3D structure as I was talking, we talked. This way, the scheduling becomes much easier for the machine or for the software, because they can just keep their operands in these two memory sets and just keep giving the instructions, next instructions to go and make this work. So this one, the only problem is this one block is actually 300,000 transistors, around 2 million polygons, and that all had to be hand constructed. One of the biggest problem we faced is that once we constructed this block, custom block, it is so massive that there is no verification tool in the world that can verify this. So we had to even write our own verification tool. Even then, there were multiple errors that we had to correct through multiple tape outs. So very large commitment, error prone, and if you are not a great expert in both analog and digital, I would not recommend trying. So we build this matrix compute unit, and then after that we build what is called SIMD, single instruction multiple data. This is used in DSP GPUs quite a bit. Think about this being like a 8-core CPU right here. And then we have built a crossbar technology to distribute the operands, as we said, one to many, many to one, to distribute the operands to itself for the next layer of calculation or to the other cores. So we combine 5 of these cores together. So each core, by the way, is running its own instruction. This is our own instruction set that we have constructed because we didn't find anything that was appropriate or that was fast enough for us. So each core can be an independent AI computer running its own AI thread. However, we do it at a cluster boundary for better ease or ease of software. With this, we are able to build a cluster. So 5 cores, they can distribute data to each other. And then we can multiply the number of cores as many times as we want. And then we put other stuff on top of that, including an ARM core or RISC-V core or any other CPU core for the control flow or for running the operating system. In our first chip, we also built a very, very innovative sensor unit, which allows this chip to work in what we call subconscious mode. Means the sensor data can come directly to the AI block, and the AI block can do just like our mind can be doing computing in very, very, very low power mode. Low power as much as a few tens of microwatts. And then wake up rest of the chip only when something is detected. So we have really tried to replicate a brain functionality. Of course, without the software toolchain, none of this works. We took very long time. Actually, the most painful part of building this type of chip is the software toolchain. We have now software toolchain that is able to take PyTorch and Onyx and TensorFlow libraries and able to map it to our hardware automatically. We also provide a reference training tool to make things work. So if one is able to program in ARM or RISC-V, they will be able to use our chip easily because it just feels like that. A compiler structure we can take from PyTorch, TensorFlow, Keras, and many other in future. We map it to ONNX right now. This is just the middle intermediate layer representation for the neural networks. And then we build our own plane for all of the data or the neural network compute. And we use LLVM for building the control plane. All of this combined into one file that gets compiled again to our hardware. So all of this has been working.
Okay.
That's it. We have many applications that you can come and see at our booth.
Well, thank you, GP. What I love about these talks is we get to cover so much ground. So we're going to have you back to do a bit of a deep dive into a few of these components. But
Please.
the other thing that I really enjoy is every once in a while, a speaker says something that will resonate in a boardroom where both the CEO and the CTO nod and say, that's what I'm thinking. And for me, this was when you said that trying to deliver perfect results with imperfect components. And everyone in the boardroom is nodding at that description. So as you're walking around CES this week, what are you most enthusiastic about for adjusting those imperfect components in the next 12 months?
So I do see a lot of promising innovations that are happening both in software and especially in packaging, Ed. I personally would have liked to see more innovation in silicon components.
Okay.
That is, CS is probably not the right forum for it. So, but what is great is people have been doing so much innovation. Agentic AI is a great example. And I think agentic AI is going to hyperpower or hyper accelerate the use of AGI in next 2 to 3 years. for the next 2 to 5 years.
That's really interesting. Danilo seems to have that gleam in his eye when I know he's got an interesting cloud. Danilo, what do you think?
Yeah. First of all, I really appreciated the flow of the presentation of GP was very instructive and educative also from my point of view. Maybe GP, you could comment a bit about, there was a conceptual slide where you shown D2A, the computing elements and the A to D. This may, in principle, this may be latency critical components, which is counterintuitive to a very fast pipeline. So maybe you could, especially with large bit depth containers. So maybe could you comment a bit around that topic, please?
Yes, Danilo, and that's where we had to actually do the innovation. The classical analog is very slow, as you said, latency. The bigger problem actually is the variability. Makes it. So we had to convert a lot of these to digital just to get the speed, and that part is actually our deep secret, which we try to, if you don't mind, try to keep. How we solve that problem is really the holy grail of companies' technology. So, but that is as you said, that is the real problem. That's why I'm sorry I made a very obnoxious comment there that if you're not an expert, don't try it. But it's kind of real.
I understand. Yeah, I understand that this is a very distinguishing point of your solution. Maybe if I could add, maybe another question could be, how do you see scalability in terms of performances with respect to the architecture you are developing?
Because of that digital conversion, then we were also we were surprised ourselves, but we have been able to solve the scalability problem. We are currently building a 2000 core device, which will, I can't give the numbers right now, but it will be much better than whatever the world has seen so far, and that will be built in 3 nanometer. So we are already halfway through the circuit implementation actually for those.
And I see we have some few minutes, maybe add. Verification, you touched this point is at all an easy job when an analog circuit is in development. So can you tell us a little bit more about, for example, deploying and validating a workload? What are the dimensions of the challenges in there?
That is actually the monumental problem. The designing, even if one is able to cross the designing phase, Danilo, as you pointed out, verification of these blocks is just one of the biggest complaints personally I have is that the EDA tools have stopped innovating in past 20 years. Innovations are, and the circuit guys are actually the biggest victim. We had to build lots of scripts or a lot of tools ourselves that were using existing tools, break the problem into many pieces. I mean, we have to break this into hundreds of pieces, verify individual blocks, but then how do you verify the connectivity among them? So then we had to write an architectural behavioral model first, Danilo, because when we try to put this onto FPGA, the FPGA just cannot take these many components because all digital implementation, right? FPGA. So verifying this was extremely difficult. And even with all of this work, we had to taper 3 times. Still bugs escaped on those boundaries. So yeah, humongous problem.
Interesting.
And that's why, anybody trying to get into this kind of area, you should be prepared. The industry is not very conducive.
Okay.
Very
We do have
interesting.
some questions from our community. Let's look at Mark's question, but for more broadly, we have a number of questions about availability of chips and different geographies. So maybe if you could help answer Mark's question, but also highlight where people can follow up to get more information on your current product line.
So first product is already there. You can come to CS booth. We have come up with a version that's called, so answer his question on the screen. GPX10 had 320 kilobyte. We have come up with GPX10 Pro, is already announced, that has more than 2 megabyte of memory. It is sufficient for most of the AGI applications, to answer your question.
Okay. And to the other questions, for those who aren't in Vegas this week, what's the best place they can go to, for example, find low power boards for India, which is asked by our friend Prasada?
Very soon we will have them also on DigiKey and Avnet type platforms. Come to our booth or just reach out to us. There is on our webpage, just send your name and question and our team will contact you. We have distributors in India, in most part of the world now, coming up soon in USA as well. So we are able to connect you to our distributors who will be able to, you just order it to us, it will be delivered to you from our distributors.
Okay. Great. And Pritam has a question as well about, it appears, a question about transistor tech.
Leveraging breakthrough in I'm sorry, but there is no break. There has not been any breakthrough in past 20 years. I mean, yes, there is some fintech gave something, but at least from technologies like me, is too little.
Okay.
Size of the chip depends on the technology node, right? So this particular one is in 40 nanometer. We don't give out the size of the chip, guys, because then people start reverse calculating the cost. So our business guys have said, sorry, you cannot tell this. I am sorry, I apologize. As a technician, I would like to tell you, but
there's always that moment when business and technology meet in the middle, right?
Yeah, and unfortunately, yeah, we cannot.
Well,
actually, if you ask me, sorry for that, the transistor. If you ask me, if somebody was to give me a lot of money and say, build what innovation you should build first, I will build that transistor. You need 0 VT transistor. Some of the parameters I'll tell you right now. 0 VT transistor is needed with very small drain and source resistance, with the voltage scalability capability all the way to at least 2 volts, from 0.3 to 2 volts. You build that transistor, that is what AI requires today.
GP, I've been told that to create such a transistor at scale, we need to wait if investment would be pushed 15 years. Is that correct in your opinion?
No, I don't believe that. It's a 5 to 7 years research. I used to work for a company called Sun Microsystem. In 1996, we were trying to build that type of transistor. So it's just the business, in at the turn of century, we started believing we have all the compute in the world that we need. Till AI came, nobody was actually asking to build more compute.
It is interesting to me how many of the conversations we've all had over the last decade come back up periodically over the years.
Yeah.
Unfortunately, we are out of time. I do want to send our greatest thanks to GP and Danilo for today. I would strongly recommend that everyone visit Ambient Scientific and other members of our community if you're at CES. If you're not, please hit the Foundation's website to check out detailed information on the San Diego event, our new certification classes, and more updates from our partners. But most importantly, we wish you all the best to our community on what should be a really exciting and innovative new year. Thank you, everyone.
Thank you very much, Ed
Thank
and
you.
Danilo. Thank you so much, guys.
Thank you.
Take care.
Thank you so much.